Back in 12.1, we talked about parametric equations. We were talking about how having one variable that affects both x and y. We can plug in t to some function and get out an x, and into another function get out y. So now what we're going to look at is instead of using just t, we're going to use two different variables, and in fact, two different variables selected in a way that it gives us an entire new way of defining points in a coordinate system. So these are going to be called polar coordinates. As it says here, like Cartesian coordinates, polar coordinates are used to locate points in the plane. So when we're working in polar coordinates, the origin is now going to be called the pole instead. And our x-axis is going to be called the polar axis, as we see there in this picture. So the polar coordinates are going to look like r comma theta. So we're still going to have two different coordinates that we use to locate our points, but now they're going to mean some slightly different things. So the radial coordinate, which is r, talks about the directed or signed distance from the origin to P. So if we have our point, we're looking at the distance from the pole to P, that's r. The angular coordinate, theta, will describe the angle that the polar axis makes with the terminal side here is going to be the ray that connects with our point here. So we're going to have the same sort of system that we did when we were talking about the unit circle back in trigonometry. So if we're talking about a positive angle, we're talking about going counterclockwise from our polar axis. And if we're doing a negative angle, we're going to go clockwise from the polar axis. And so because of that, as we remember from the unit circle, there's lots of different ways that we can then describe the same point. Right, so every time that we go around the unit circle once, remember that that's going to be an angle of 2 pi. And so we can actually get the same angle by either sort of going straight to it from the polar axis, or by maybe going all the way around the circle and then meeting back up with it. That's going to be two different angles, and so two different theta values, but it'll make the same point as long as r is the same. And so to generalize, the coordinates r theta and r theta plus or minus 2 pi will talk about the same point, because that's going to be some extra cycle around the unit circle. Second, as we see here, the radial coordinate may be negative. So what that means is the points r theta and negative r theta are reflections of each other through the origin. So as we see here in this last picture, if we take r comma theta and we take the same theta and then instead sort of go backwards through the pole, that same r direction, that gives us our negative r equivalent. Right, so what that means is if we were to instead go all the way around this way and then have a negative r, we would end up reflecting back up to our P here, which means that, as it says here, r theta, negative r theta plus pi, and negative r theta minus pi will all refer to the same point. The origin is going to be any point as long as we have 0 for r. Any angle at all fits in there. We're still at the pole because we're going a distance of 0 from the pole. So we'll go ahead and take a look at what a point looks like in polar coordinates. So we got this point Q, and we want to show it in polar coordinates. So remember that our representation here is given by r comma theta. And so we're talking about a distance of 1 from the pole here, which, as you can see, our polar coordinate system will use these concentric circles. These indicate distances from the pole. And we'll also have these diagonals will represent our sort of major angles when it comes to the unit circle, right? So we have something like pi over 6, pi over 4, and then this big one here is pi over 3, and their equivalents in the different quadrants. So what we're looking for here is 1 5 pi fourths. So we're looking at the inner circle here. This is a distance 1 from the pole. 5 pi fourths, remember if we go 4 pi fourths, that's going all the way over to the negative x-axis. We'll go 1 more pi fourth. So we're looking at going down here. And so 1 away on that circle will be point Q. All right, so if that's Q, as it says here, we want to give two alternate representations for that same point. So let's think about some different ways that we can do it. All right, so as it sits now, we started from our polar axis and we went counterclockwise in the positive direction, 5 pi fourths. All right, so let's think about what happens if we would have gone negative instead. If we would have gone negative, r is the same, right? So we'd still have 1. But instead, we'd be going 1 pi fourth, 2 pi fourth, 3 pi fourths. But we're doing it in the negative direction, so we put a minus on that. So that's going to give us the same point, but from a different direction. All right, let's think about another way that we can get this same point. Remember, we have that sort of tactic of using negative r. So let's try putting -1 and seeing what our angle should be. Right, so if we had a negative r, we would end up being reflected over up here. Right, so if we would have just taken q, put a negative there, it would give us this point. So to go the opposite direction, we'll make this point, figure out that angle, put the negative on the r, and that'll bounce us back to q. So this angle here is just pi fourths. So we think about that, we go pi fourths, and instead of going 1, we go -1, so we jump sort of back through the pole down that way. And as you can see, this matches up with the representation we said earlier. This is going to be -r theta minus pi, right? 5 pi fourths minus 4 pi fourths. Okay, and so we'll repeat that then with something a little different here. We've got one that already has a negative in our radius, right? So we're going to be, again, on this first circle here from the pole. We're going to go around 7 pi fourths. Remember, that's 1 pi fourth from a full rotation. But instead of going down this way in the bottom right here in quadrant 4, we have a -1 up there. So we're going to jump back through the pole into quadrant 2. This will be r. So that's going to be r. Again, we want 2 alternative representations. So one thing that we can do here is add a rotation. So we can take 7 pi fourths and add 2 pi is going to be 8 pi fourths. So if we just add those together, we get 15 pi fourths. And we know that that's going to be 1 full rotation. Too much. 1 full rotation plus a bit, and then we'll jump back through to r. Right. Surely there's got to be a way then to write r with a positive radius. And so that's just going to be a matter of going straight to the ray that r is sitting on and figuring out what is this angle now. It's 1 pi fourths short of a half turn here. So we're looking at 3 pi fourths. All right, so let's look at one then that has a negative on the angle. This one also has a 2 for the radius, which means that we're going to be jumping out to the second circle from our pole. And we've got -3 pi halves, which means that we're going to be going clockwise. So we'll be going up to the positive y-axis then. It'll be going 2 away from the pole, which means we're up here. This is point S. And so we'll go ahead and then follow the same sort of pattern as before. If we want to keep the same radius, we'll either add or subtract 2 pi. We'll go ahead and let's just add 2 pi here. We get pi halves. If we want to have the negative radius, we'll go ahead and add or subtract just pi. So maybe negative pi halves here. So that's a general sort of way that we can find what points look like in polar coordinates. But as I said, this is a version of parametric coordinates. So how do we sort of tie this back in with x and y? Well, there's going to be a conversion based on what we know from the unit circle, in fact. So if we have a point in polar coordinates, right, we have an r, the distance from the pole, and some theta. We can convert to x and y just by sort of reframing this to look at the horizontal and vertical components. Right, so that makes a triangle, one that we're very familiar with from trig. It looks like what we were dealing with a lot when we were dealing with the unit circle. Right, and so we'll have sort of the same relationships that we did back then. So if we have a point with polar coordinates r comma theta, then x is going to be r times cosine of theta. Let's think of why that's true. The cosine of theta, that's adjacent over hypotenuse, that's x over r. Multiply both sides by r. And that's how we get that relationship. In the same way, we get y equals r sine of theta. Right? And so when we do that, we should be able to convert to x and y. Right? That's what makes this parametric then. We can find that with r and theta. We get our x and our y. We can also go backwards. right? We have the relationship that r is a set distance from the pole, which means that any of our points are going to sit on some circle of radius r. So we have that r squared equals x squared plus y squared. And then likewise, we have the relationship with theta, y, and x, where the tangent of theta is opposite over adjacent, so y over x. So we'll go ahead and see how this kind of plays out. One thing to keep in mind is that when it comes to points in our rectangular coordinates with x and y, we only have one representation for every point. Whereas when it comes to polar, there's multiple. So we'll see how that kind of comes to play when we are using these different conversions. So if we've got these polar coordinates, we've got r theta, right? We look at x, that's r cosine of theta. So if we take the cosine of 3 pi fourths, right, the best way of thinking of it now is to actually rationalize the denominator. We'll call that root 2 over 2. It's 3 pi fourths, which means that we're going to be in the second quadrant, which gives us a negative. So we get negative root 2 for x. And then for y, we're looking at 2 sine of 3 pi fourths. Again, 3 pi fourths being in quadrant 2 gives us a positive sine value. And so we get positive root 2. So our point would end up being negative root 2, comma, root 2. And we can kind of check here, negative x value, positive y value. That gives us something in the second quadrant, just like 3 pi fourths with a positive r value will give us something in the second quadrant as well. And so the sine on our angle will affect, the sine from the trig function of our angle will affect the sine on our x and y values. And so that will kind of lock up all of those different possible representations for a point in polar. When we take the cosine of the sine, it'll always put us at some value in between negative 1 and 1. And so it'll wrap up that whole idea and always give us sort of one option for x and one option for y. So let's go backwards. If we're going to take something that's got Cartesian coordinates 1 and negative 1, and we're going to express that in polar coordinates, we'll go ahead and see what happens there. Right, so we have our x and a y. So we'll go ahead and do each of these different components of our polar stuff. So we've got 1 squared plus negative 1 squared. So r squared is 1 plus 1, we get 2. And so r will be equal to plus or minus root 2. Right, so we have a couple of options here. And so we're going to have to pick and choose which one that would make sense for this particular point. So we'll have to find the theta that matches and sort of pick the right combination. So the tangent of theta will be negative 1 over 1. So the tangent of theta is negative 1. We take the inverse tangent of both sides. And so we think what's an angle that gives us a theta value, or sorry, a tangent value of negative 1. And so we're looking at 3 pi fourths and let's see, 7 pi fourths. And each of these will be plus or minus 2 pi n, where n is a natural number. So we have an infinite amount of thetas possible here. And we have one in the second quadrant and one in the fourth quadrant. So we have to decide, are we doing the second quadrant with a negative, maybe the fourth quadrant with a negative, second quadrant with a positive, fourth with a positive? We have to go back up here and look at which quadrant does this point sit in. Positive x value, negative y value, that's quadrant 4. So at this point, all we have to do is pick r and theta so that our polar point ends up in quadrant 4. Simplest way to do that is just to pick the positive r and a theta in quadrant 4. And we'll just pick the first one, 7 pi fourths. And again, we could pick any sort of rotation of 7 pi fourths, like 15 pi fourths, 23 pi fourths, and so on. Or we could have picked negative root 2 and picked maybe 3 pi fourths. It should all be the same. What's important is you pick the right combination of positive or negative r with r theta in the correct quadrant. So definitely a lot more straightforward to convert from polar to Cartesian since there is only one option. But we do have a lot more freedom in picking our polar coordinates, and maybe we can pick something that's more advantageous to us in some cases. So now that we have both points and sort of conversions when it comes to polar coordinates, we'll start talking about curves. So when we're talking about curve and polar coordinates, we're talking about points that satisfy an equation in r and theta. So talking about that distance still and the angle. So let's think about what happens if we have r equals 3, right? It's satisfied by the set of points whose distance from the origin is 3. So what does that remind us of, right? The angle is arbitrary, it's not specified, so the graph is a circle of radius 3 centered at the origin. So as it says here, r equals a describes a circle of radius a centered at the origin. Right, so if we have r equals some just constant, we get a circle. Radius is that constant, well, the absolute value of that constant. So let's talk about when theta is equal to just a number. All right, when we have theta equal to pi thirds, it says it's satisfied by all the points whose angle with respect to the positive x-axis is pi thirds. R is unspecified, so we do not care what the distance is from the pole. And so pi over 3 is the line through the origin, making an angle pi over 3. And so whenever we have theta equal to some constant, we're talking about a line going through the pole, and it makes an angle with the positive x-axis, whatever theta sub 0 is. And so that makes sense. If we look back here at our polar axes, and we think about what a blank Cartesian plane looks like, right? We usually have these vertical lines and the horizontal lines that make up our grid, right? These are different x equals constant lines making our vertical lines and y equals constant lines making our horizontal. So in the same way, these are our r equals constant quote unquote lines. And these guys are our theta equals constant lines, these diagonals coming out here. So it all kind of works the same way. So let's go ahead and look at r equals 6 sine theta. So looking down here, it looks like we should be getting some sort of circle. But we'll go ahead and what we'll do is convert this polar equation into our Cartesian equation and see what that particular equation will give us. So we'll go ahead and look at, first off, how are we going to convert? Well, when we have r, that's not particularly helpful. We either want maybe r squared or maybe r times a trig function. That's the only way that we'll be able to convert r into some sort of x or y combination. Similarly, with sine, we don't really have any way of just converting that. We like to have an r associated with it. So what we'd like to do here is let's just multiply both sides by r. That gives us r squared on the left and 6r sine theta on the right. And now we can convert. R squared is x squared plus y squared. And then we have r sine theta is y. And so we'll go ahead and move our y term to the other side, complete the square. So we'll add, let's see, 9 to both sides. And we'll factor this guy, y minus 3 squared. All right. So what that gives us then is a circle, radius 3. Go ahead and write that down. Radius 3, sitting at 0, 3. And here we are, 0, 3, radius 3. And that gives us our circle. So when we're able to convert, we can see exactly what kind of curve we're able to look at without too much trouble. And so we'll look at the same sort of thing here. We'll look at some different examples of these curves and kind of get an idea for what these guys look like in general. So first off, r equals 7. This is just a circle of radius 7. Centered at the pole. And so we'll go out 1, 2, 3, 4, 5, 6, 7, and just follow the grid line. Definitely not perfect, but you can tell what I was going after. Right, and so for the second equation, r squared equals 4r cosine of theta, following the same pattern as that last problem. And so we get 4x on the right side, x squared minus 4x plus y squared equals 0. Complete the square. So we'll go ahead and add 4 to both sides. So x minus 2 squared plus y squared equals 4. So this is a circle of radius 2, sitting at 2, 0. There we go. And then this last one here, r squared equals negative 7 r sine of theta. X squared plus y squared equals negative 7y. X squared plus y squared plus 7y equals 0. And this one's going to be a little bit more difficult. Remember that we're going to want to divide by 2 and then square. So we're looking at 7 over 2 squared, so 49 over 4. So we're looking at y plus 7 halves squared equals, well, we'll just say 7 over 2 squared. So we're going to go down 3.5. 1, 2, 3.5. And then our radius will be 7 halves, so we'll go all the way back to the origin and out to 7. More like an oval than a circle. Let's try that again. That's a little better. So we can kind of see what we'll end up with. Whenever we have a number in front of a trig function, then depending on whether it's cosine or sine, will either be lined up with the x-axis if it's cosine or the y-axis if it's sine. Right? If it's a positive number up front, that's the distance here, 4. If it's a negative number, that's the distance down, or if it was in front of the cosine, it'd be left. This is 7. And here's our summary of that. So we have r equals a. Here's our circle radius, absolute value of a, about the origin. If we have 2a sine theta, we're going to be going along the y-axis. If a is positive, we're going to be above it. If a is negative, we'll be below. And so, we can say that this distance, the diameter here, would be a. If we have cosine instead, we're along the x-axis. So that's going to be a generalization for these particular types of equations, but there's definitely more possibilities, and we'll have to figure out some other way of figuring these out. So say we just want a graph. It says choose several values of theta, calculate the r values, tabulate the coordinates. So what that's describing is just a t-chart. So we want to be strategic and pick sort of some good theta values and go ahead and put those on our chart here. So we definitely want to get everything from probably thinking about the period of sine, everything from 0 to 2 pi that we're interested in. And thinking about which values sort of play nicest with sine. Probably the pi over 6 guys. So we'll use pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi halves, and finally 11 pi over 6. Right, so 0, we get 1 plus 0 is 1. 1 plus 1 half is 3 halves. If we have pi halves, it's 1 plus 1, we get 2. 5 pi 6, we get 3 pi halves again, or sorry, 3 halves again. Pi makes sign of pi 0, so we get 1. Then we start subtracting, right? 7 pi 6 gives us a negative 1 half. 3 pi halves, we get 0. 1 minus 1. 1 half again. And then we complete the period. We should get 1. So first we've got theta 0, r is 1. That puts us right here. Then we're looking at pi over 6, 3 over 2. So pi over 6 is this first line. Will be exactly halfway between the first and second circles here. Pi halves gives us 2. Then we'll basically do a reflection over here. And then when we start getting to our 7 pi 6, we get 1 half. So halfway in the circle here. 0, halfway in the circle there. And so we'll go ahead and connect. And so that'll give us our graph. And this is going to be called a cardioid because it looks kind of like a heart. Right? And so we got that from 1 plus sine of theta. And so it's going to be a little tricky to kind of figure out what is adding a number to our trig function, or maybe adding a number and multiplying kind of give us. So we're going to have to rely on some sort of method of relating r and theta. As it says here, an alternative method is to graph r equals f of theta as if r and theta were Cartesian coordinates, where theta is horizontal, r is vertical. So basically just to treat this as an input-output, theta is the input, r is the output. As it says here, we need to choose an interval on which the entire polar curve is produced. So we're going to use then that graph as a guide to sketch our theta on the final polar curve. So as we see here, we have two different graphs. So what we're going to do is we're going to treat this like an r versus theta graph. And we're going to graph 3 sine of 2 theta here. All right, so let's examine this graph as if it were sort of just x's and y's. All right, 3 is the amplitude. And the period involves this guy here. So we take p equals 2 pi over whatever this number is. So in this case, it's 2. So our period here is just pi. Sine, we start and end at the midline. And then we'll go up, midline, down, midline. And so graphing one period will look like this. Or approximately. All right, so let's just start here and see what happens. So first off, we start out with r equals 0 when theta is equal to 0. There we go. So the pole. We go up to the point at, it looks like pi fourths, we go to 3. So pi fourths 3 is a point. And then we go back to 0. So we have to figure out what happened in this, all this in-between space. So it looks like our angle is increasing as we go from left to right. So we think about it this way. As we're going from left to right on this graph, we are going counterclockwise in a circle on this graph. So we're going, our r is increasing as our angle is increasing. So maybe something kind of like that. Then our r starts to decrease. Our angle is still increasing. So by the time we get to pi halves, we get back to that same pole. And so in this space here, we end up with this loop. So let's talk about what happens after that. From pi halves to pi, we get the same situation. We're starting and ending at the pole. At 3 pi fourths, we get -3. So what's happening is our graph is actually falling below 0. So instead of being up here, although our angles are between pi halves and pi, all of our radii are negative. So we're going to end up down here. So we'll go ahead and graph this point. At 3 pi fourths, we get -3. So we go 3 pi fourths, jump back through the pole, 1, 2, 3 down here. And so we'll end up making the same sort of shape as we did before. And that'll be then this particular section here. There we go. This definitely doesn't look like the whole story, right? We've only really gone, as far as our thetas are concerned, from 0 to pi. Although we've completed a period, we haven't finished the curve. We haven't gone from 0 to 2 pi in terms of our theta here. So we're going to actually have to go again. So we'll go ahead and do this one more time. There we go. Happy with that. All right, so let's talk about the next section here. We're going from pi to 3 pi halves. We have a positive r. So pi to 3 pi halves is the third quadrant. Positive r means that's where we're actually going to stay. And again, our r is increasing all the way up to, we have this point here, 5 pi halves, 3. So as we are making our counterclockwise loop, our r is getting bigger and then getting smaller again. And so we have this loop. And so we can imagine then what the last little bit would be. 3 pi halves to 2 pi, right? Those are usually fourth quadrant, but our r is negative. So we're actually going to think about what happens as our r is sort of going backwards in the second quadrant instead. Right? So we're going up and around this way. And so let's go ahead and recap the direction here. We start out by going counterclockwise in this loop. Then we fall down to the green here. And again, going counterclockwise. We circle over to this multicolor loop here. Still counterclockwise. And then lastly, we end up on the more purpley multicolor loop, still counterclockwise. And so we get what's called a rose curve with 4 petals. So a 4-petal rose curve. And so that's how we can use the graph of r versus theta to get our polar graph. So let's take a look at what happens then if we have sort of an extra piece added on here. Remember, if we're talking about taking an extra number and adding it or subtracting it to our graph, we're talking about raising or lowering the midline. So in this case, the midline is going to be at r equals 5. We also see that the amplitude is 5. Or rather, -5. So our, let's see, our midline is going to look like this. And we see here that we have no sort of object changing the period, so we'll go ahead and just go up to 2 pi. And I'll kind of pick the regular, back when you were first learning about graphing these guys, pi halves pi, 3 pi halves 2 pi. So we start out at the midline for the sine function. We have a negative as our amplitude, so we're actually going to go down, back up to the midline, go up, and then down again to the midline. So there's our graph. We start at theta is 0, r is 5. So there's theta 0, r is 5. We're going to have our r is going to decrease until at pi halves we hit 0. So let's go ahead and represent that. So that's where r is 0. Then go ahead and look at what's happening here. We've got pi as our angle. We're going back up to 5. So 1, 2, 3, 4, 5. And our r is going to just be steadily increasing the entire time. And it will keep increasing all the way until 3 pi halves, and this is 10. So all the way down here, 3 pi halves 10. So r is going to keep increasing, increasing, all the way down here. And then r is going to start decreasing again, back down to 5. Not doing a very good job with showing that. There we go. Better. All right, so that's going to be our graph here. So what we can kind of gather then is this is another cardioid. We had a cardioid back here. Think about what was in front here. This was a 1. So we had 1 plus 1 sine of theta, 5 minus 5 sine of theta. Here we had a cardioid where sort of the dimple was underneath the y-axis. Here the dimple is above, and the rest of the graph is below, because we have a minus here. So when these numbers match, we're looking at a cardioid. If there's a negative in front of sine, most of it's going to lie underneath the axis. If there's a positive, it's going to lie on top. As you can imagine, if it was cosine instead, it'd be to the right. And this one, the cosine would make it to the left. So let's look at what happens if maybe those numbers don't match. We have a 2 and a 4. See back here, notice that the dimple happens because our graph touches and bounces off of the theta axis here. But let's think about what happens when we have r versus theta in this situation. So midline's at 2, amplitude's 4. So 1, 2, 3, 4. 1, 2, 3, 4. So it looks like we're going to need to use some negative r's, which is going to change things. So we've got cosine of theta. Again, there's nothing changing the period. So we'll go ahead and use sort of the standard intervals. With the cosine, you start at the top, hit the midline, bottom, midline, top. So there's our graph. And let's talk about what happens. When theta is 0, r looks like 6. Right, r is going to decrease to, at pi halves, r is 2. Right, Then we end up with some little distance here, and all of a sudden our r goes negative. So it might be helpful to pick out where does this graph hit that axis. So that's where 4 cosine of theta is -2, so cosine of theta is -1/2. Right, we have two places that we see that happening. We're looking at, looks like 2 pi thirds for this one. And this one's going to be about 4 pi thirds. So at 2 pi thirds and 4 pi thirds, we hit r equals 0. So it'll be kind of tangential with this line here, if at all possible. There we go. And so in between, we see that we hit the point. We've got pi -2. So we go around to pi, jump back through the pole, this one right here. So we've got to get from here to here. Meanwhile, our theta is still marching along. Right, so we think about what would happen. We're still going counterclockwise, so it looks like we got to go like this. Right, so our r grew to a -2, so here we're getting further away from the pole. And then we're going to shrink back again to 0. And we're going to shrink back to 0 right here. Try to make this as symmetrical as I can. So right along this, the flip of our 4 pi thirds here. So 4 pi thirds of this line, we flip it back here. That gives us where we want to sort of tangent with. There we go. Then we get to 3 pi halves, and we're back at 2. And then we get to 2 pi, and we're all the way back at 6. So we're going to grow back again. And so here we get a limison with a loop, is what it's called. And it's like a C with a little tail on it. And so that loop is caused by this little section right here, where our radius turns negative. All right, so that was a couple cases where we had a number plus our trig function. In both of these cases, and in fact back up here as well, we had our period was just 2 pi. We saw that when our period is not necessarily just 2 pi, we end up with some more interesting shapes where we maybe hit the pole maybe a bit more often. Okay, kind of that repetition in each quadrant. Right, so let's talk about what happens when we have maybe something even stranger happening on our period. Right, so if we look at cosine of 2 theta over 5. Right, so we think about what are the pieces that we need. First off, the period of this is going to be 2 pi over the coefficient here is 2/5. Flip, multiply, we get 5 pi. So our period is 5 pi. Right, so we'll go ahead and think about what do we need to generate the entire curve. So if we just look at theta going to 2 pi, which we know is necessary, we know we need to eventually get back to the original sort of starting point. If we look at theta going to 2 pi, in this case, we only get what appears to be around, not very much of this graph. If we go the whole period, then we end up all the way over here at, we think about what happens if we plug in 5 pi, right? We end up with cosine of 2 pi here. We go back to 0 there, and it's still incomplete. So what if we look at the least common multiple of 2 and 5, we get 10. If we look at that, then you can see that we go all the way around and sort of complete the shape in each quadrant and end up back where we started. So that's important. In general, as it says here, an interval 0 to p over which the complete curve is guaranteed to be generated must satisfy two conditions. P is the smallest positive number such that P is a multiple of the period. So P has to be a multiple of the period so that the first output and the last output match up. Sorry about that. So that the first output and the last output match up. So we need that first, so that the radii are the same. Right? First, we need that. Second, we also need that P is a multiple of 2 pi. That's so that since we have the same radius, we get the same angle as well, that we can end up matching with our original 0. Right? P has to be a multiple of 2 pi so that these guys are the same. Our theta end up with the same point there. So if f of 0 is f of p, the radius is the same. These are actually backwards. This should be f of 0, 0 to be r theta. And f of p, p. So the radii will be the same. And since theta is a multiple of 2 pi, we'll end up matching with the original point. So in general, we're looking for the least common multiple of the period and 2 pi. That's going to be p. In general, polar rose curves have equations of the form r equals a cosine of k theta or a sine of k theta. A is greater than 0, k is a positive rational number. The length of each petal is a. So looking back up here, the length of each of these petals in this case was 3, right? Because we peaked at 3, so we go out 3. So the length of our petals is a. The number of petals is determined by k. If k is even, this is important, if k is even, there are 2 k petals. If k is odd, there are k petals. If k is not an integer, the number of petals is more complicated. And so we have a chart here. So here are rose curves with rational k. So let's talk about this looks very complicated. Let's talk about what we'll actually focus on. Pretty simple. We'll just talk about this. So actually, let's wrap that up a little bit better. So we'll talk about just really whole numbers multiplied by theta as far as like tests and stuff like that go. So I guess technically we will be talking about this diagonal since it's all just 1. But these look very nice. These look cool. We're not going to be necessarily working a whole lot with them. We're going to focus on the whole number side of things. It'll be good to just be, kind of aware that these exist. All right, so that will then wrap up our section on polar points and curves. What we will do next section is we'll actually start doing calculus on these polar curves.